Okay, in yesterday's session, we have discussed about the common emitter configuration. Okay. Okay. So before we have discussed on the common emitter configuration, we have discussed one effect called as early effect and also called as punch-through effect. Right? So this effect is going to take place especially in a common base configuration. And whenever you are increasing the reverse bias voltage, that is especially the VCC or VCB. So whenever you are increasing this reverse bias voltage, the base width modulation, that is the width of the base will be get so much of narrow, and we are going to call that effect as the early effect and also called as base width modulation. If we are still increasing the reverse voltage so much up high, therefore at one value of the voltage, this base will be get vanished, and what happens, this breakdown is going to take place in a transistor, and that breakdown and that effect is called as punch through effect. That is, it is going to mix the N and N transistor completely. So that is not actually the that is not the required case. That is, if the breakdown is going to occur, then we are going to call that as a punch through effect, which is going to take place in common base configuration. So just I'm trying, I will try to revise what we have discussed in yesterday's class. In the common emitter configuration, emitter is common between the input and output. Okay, that means base is going to act as an input, collector is going to act as output. You see, this is actually an NPN transistor, and this is actually the VB is the input voltage and IB is the input current, and similarly here VC is the output voltage and IC is the output current. Always for every configuration, we are making the emitter based junction as a forward bias, collector based junction as a reverse bias. So we need to draw the input and output characteristics of every configuration. Okay, that is our objective for every configuration. But this common emitter configuration also, we need to draw the input and output characteristics. Okay, so for the characteristics between the input voltage VBE and the input current IBE. So we have drawn this one, see here. So input voltage is VBE and input current is IB, which it will be very less amount of current, that is in terms of microamperes. So these are the characteristics which follows the forward bias characteristics of the PN junction diode. So when the voltage is increasing, this characteristics are moving towards the x-axis, that is, it is moving to the right hand side. So why it is moving? Because whenever this collector voltage, collector emitter voltage, whenever this VC is increasing, the base width will be get so much of narrow because you are increasing the reverse bias voltage. So whenever you are increasing this reverse bias voltage, this base will be so much of narrow. So therefore, what happens? This base current will be get decreases. So that is the same. For every increase of the VC voltage, the base current value is going to get decreased. So this is actually the input characteristics. Coming to the output characteristics, in the output characteristics, which is drawn between the VCE output voltage and IC as an output current. Okay, so in this active region, we have drawn for all severe regions, but in this case, the collector current is not at all a constant. Whatever you have seen in the common base configuration, where the collector current is a constant, but in this case, it is not a constant. It is varying with respect to the output voltage VCE. That means whenever you are increasing the VCE, the collector current is also increasing. Why the collector current increasing? The collector current is increasing just because whenever you are increasing this VCE, that is collector to emitter voltage, that means you are increasing the reverse bias voltage. So whenever the reverse bias voltage is increasing, the depletion layer of the collector base junction will increase, which makes the base width as a narrow. So therefore very less recombination is going to take place, and most of the electrons from the emitter junction will pass to the collector junction through base. So therefore, not just a 95%, 98% of electrons are going to pass, and therefore the collector current is going to be get increased. So this is the situation where the collector current is increasing, and this is alpha is the gain for a common base configuration. So every gain formula is output current divided by input current. That is, if you are discussing about the current gain, output current divided by input current. We are denoting with alpha in case of common base configuration, which this value is approximately equal to 1 or or less than 1, because the numerator, that is the output current, as well as input current, both are indicated with milliamperes only. But that is not in the case of common emitter configuration, because in the common emitter configuration we are using the beta as a current gain. So but in beta is equal to the output current IC divided by the input current IB. But IC is indicated with milliamperes, but IB is not indicated with milliamperes, because of very less amount of IB we are indicating with the microamperes. So therefore this uh, milliamperes divided by microamperes will be approximately in the range of kilo. Therefore this value will be approximately 500 to 1000 like that. So this is a large signal. So for that reason, for amplification purpose, we are going to use common emitter configuration. Always for amplification purpose, we are going to use the common emitter configuration because the beta value is very high. Okay. Now let us try to discuss about, this is about the common emitter configuration. There is yesterday's hour. Now let us try to discuss about the common collector configuration. What actually common collector configuration? Common collector configuration is the same configuration, but whereas the collector is common. If you see here, the collector is common. The collector is common between the collector is common between the input and between output. Okay, we are going to call it as a common collector. Okay. So this is actually the same thing. The collector is common between the input and between. What is the input voltage? If you want to draw the characteristics of input and output for the common collector configuration, you need to know what is the input voltage and output voltage, input current and output current. So what is the input voltage? Input voltage is the voltage difference between the base and the collector now. Therefore, the voltage difference between the base and collector is VCB. So VCB will give you the input voltage, and the current flowing through the base junction, nothing but an IB, is nothing but an input current. So therefore, you need to draw the characteristics, input characteristics between the input voltage VCB and the input current IB. So coming to output side, output is not now collector, output is now emitter. Therefore, the emitter collector voltage or the collector emitter voltage you can see here. So this is VEE now, because you have connected the battery to the emitter of the emitter junction of the transistor. So the emitter, now the output current is the emitter current and the output voltage is VCE or VEC. Okay. So to find out the voltages and input and output voltages and currents, we are going to use this voltmeters and ammeters. Okay. Voltmeters are in parallel and ammeters are in series. So now we need to draw the input characteristics between for input characteristics between the VCB and IB, because that is the output, that is the input voltage and input current. So let us try to draw the input characteristics. So if you are trying to draw the input characteristics, see here, I will show you here. Okay, so these are nothing but an input characteristics. Okay, please just neglect the left hand side diagram. If you are observing this input characteristics, if you observe here input characteristics, what happened? This is actually the collector base voltage VCB, and this is, that is input voltage, and this is the IB in terms of microamperes. Now, so for every one fixed value, if you see one fixed value of the voltage, you have one value, and this value is different. That is, if you perfectly see here, so what happens at one value of the VCB, considering VC as a constant for one value of the voltage, approximately you can consider it as a 5 volts or a 10 volts. If you want, you can consider it as a 5 volts. Just consider it as a very less value, that is 5 volts. So for a 5 volts of VCE, what happens? The VCB, whenever we have a VCB at one point, the IB value is this one. Okay, the current is this one. Okay, at position 1. But whenever you are increasing the VCB, what happens? The current value is decreasing at a position 2. Right? So why it is decreasing? Whenever you are increasing the VCB, the base current is decreasing. Right? So why it is decreasing? Why it is decreasing, which we have already seen in the yesterday's hour. That is, if you see VCB, what is actually VCB? So VCB, I will write the equation here. If you see here, VCE is equal to summation of VCB and VB, right? So the equation is not going to change for every, either it is a common emitter, common base, or any configuration. The VCE is equal to VCB plus VB. Okay. Now what are you doing? You are increasing the VCE. That means you are increasing the VC. So sorry, you are increasing the VCB, right? You are increasing VCB. So how is going to possible to increase the VCB? That indicates that you are increasing VC. So when that means you are increasing the reverse bias voltage. Whenever you are increasing the reverse bias voltage, this depletion layer will increase. Okay, the same thing. Whenever you are increasing the reverse bias voltage, this depletion layer will increase and make again the base as a narrow, and making again the base width as a narrow. Okay, therefore, just because of this increase of this common to base voltage, VCB, the base is getting narrow. Therefore, what happens to the base current? Base current will be get decreases because there is very less recombination of electrons and holes are taking place. Therefore, the base current is decreasing from this point to this point. So whenever you are increasing VCB, right? So this is actually for one condition, that is when VC is equal to 5 volts. Now what am I doing? I am increasing from VCE1 to VCE2. That is, I am increasing the voltage now, not to 5. Now it is not 5 volts. Now it is 10 volts. So whenever I have increased the VC to 10 volts, now it is moved. Now the axis or the characteristics moved to the right hand side, right? So now it is here. Now this position, it is here, right? Now it is here. So that means whenever you are increasing the VC voltage, VCB is also increasing. Can I say that point? Because I have increased VC from 5 volts to 10 volts. When I'm increasing, the axis is moving to the right hand side, which it increases also the VCB, right? That means how it is going to be done? Because I have already told the same equation, that is VCE is equal to VCE plus VB. VC is equal to VCB plus VB. That means what you are increasing now, you are increasing VC. So whenever you are increasing VC, automatically VCB will also increase. So that is the thing here happening whenever you are increasing the VC from 5 volts to 10 volts. That is, it is moving from this point to this point. Automatically the VCB will also increase. That is to this point. If there is no effect, means it will be lie down on here only, but it is not lying at here. It is increasing. So if you want to draw the axis of 15 volts, it will increase. If you're drawing for 20 volts, it is going to, that is, it is always moving to the right hand side. It is not shifting to either x-axis or y-axis, but it is, the characteristics are moving completely to the right hand side. Okay, these are nothing but an input characteristics. Okay, so these are the characteristics which it is drawn between VCB and IB, and whenever for a fixed VC of voltage, whenever VCB is increasing, the base current is going to decrease, which we have discussed. And for a variable VC voltage, that is, if I am changing the voltage from 5 volts to 10 volts of VC also, VCB will also vary. Similarly, the IB will also vary, right? So therefore, these characteristics are going to move to the right hand side completely. Okay? So this is about the input characteristics. So these are the characteristics. If you see here, the same thing we have represented here. VEC or VC for 2 volts and 4 volts. So this is the 2 volts. I'm increased from 2 volts to 4 volts. These have been increased. And again 4 volts to 6 volts, it is going to increase. So which it increases the VCB voltage, and it is also decreasing the base current from starting point to ending point, right? So this is input characteristics. Now coming to the output characteristics, what actual output characteristics are? Output characteristics means we need to draw between VCE is the output voltage and I is the output current in this time. So we need to draw between. So these are the output characteristics. If you see clearly, these are the characteristics which it is same as common emitter configuration. If you observe clearly, these are the characteristics same as common emitter configuration. So which we have discussed yesterday. So this is same as common emitter configuration. Because, so what is actually y-axis in that case? Shall I open that common emitter configuration? Yeah. if you see, this is for a common emitter configuration. In the common emitter configuration, what happened? So this y-axis is the collector current, x-axis is VC, right? But in this case, x-axis is VC, which it remains same, but the y-axis is not IC, but it is IA. This is IA. So what is the difference between the emitter current and collector current? It is not going to differ that much. If you are considering the gain as approximately equal to 1 or something, what happens? The emitter current is equal to collector current. Okay, is approximately equal to collector current. Therefore, the characteristics what you're going to look will be same. Output characteristics will be same in case of common emitter configuration, common collector configuration. Only the y-axis, the currents will be get changed. That's it. Okay, in that case, it is collector current, and in this common collector configuration, it will be emitter current. That's it. So everything that is the active region, saturation region, everything, the operation, everything is same. Cutoff region. Okay. So I have already told why it is not maintaining it as a constant in the previous configuration itself. Okay. Whenever you are increasing the VCE, the base width is going to increase, and the emitter current will also increase. Madam, emitter current increases, collector current is also going to increase. So these are the input and output characteristics of a common collector configuration. Okay, this common collector configuration is also called as emitter follower. Okay? The common collector configuration is also called as an emitter follower. These are for everything, that is for every configuration you need to discuss about. First of all, you need to draw the diagram just like what it is there in the lecture notes. After drawing the diagram, you need to write down you need to draw the input characteristics, and you need to write down at least 2 to 3 points regarding the input characteristics. Then after, you need to draw the output characteristics, and you need to write down at least 2 to 3 points regarding the output characteristics. Also, you need to derive or you need to find out what is the gain. Okay, what is here in this case, if you see, the gain is the current gain. Current gain, we are going to use it as a gamma in the common collector configuration. What is output current? What is the output current in this case? Output current is the emitter current, and the input current is the base current. Okay. So this value will be also more than 1000 like that. Okay. So this is the current gain formula gamma. Okay. So I can choose for the best amplification. We need to choose only the common emitter configuration. Okay. So these are the 3 types of configurations: common base, common emitter, and common collector configuration. Okay. And I will try to do the comparison, but before going to do the comparison, I want to discuss also another concept in a common collector configuration. So that concept should not make you any confusion. Please don't get confused with respect to this concept. See, so usually for AC biasing, we will have 2 types of biasing. I think you already know. We have 2 types of biasing. That is, if you are connecting AC at the input and output side, you're going to get, we are going to call it as AC biasing. If you are connecting DC, then we are going to call it as a DC biasing, right? But in case of AC biasing, you can make the collector here itself, making it as a common to input and output. But whereas in a DC biasing, if you see, this is an AC. But if you see for a DC biasing, this is actually we took emitter. Okay, and we are not saying this emitter is common. Collector itself is common, but we are collecting the output here. Okay, we are collecting output here, but not here. Okay, this is actually the output voltage. This is actually, if you see the configuration of this one, you should not say that this is a common emitter configuration. No, if we have a resistance internal, the emitter resistance is available, means that indicates that this is a common collector configuration only, but not a common emitter configuration. Okay, please don't get confused. And we are redrawing the circuit. That's it. Just we are shifting the collector to upward and emitter to the downwards. Okay. So if you see, same thing I'm showing here. See, for AC signal, they are going to use like this. That is, to amplify an AC signal, they are going to give an input voltage here, AC, and they are going to collect the output voltage here, AC. Okay, they are going to AC. So for an AC signal amplification, they are going to use this circuit, and this circuit is not a common emitter, it is a common collector. Common collector, you are taking the output at the emitter side. Okay. So for a common base, what you're going to do, for a common base, you are considering the output as, okay, we'll discuss in the comparison. Okay. So this is the input resistance, and this is an output resistance, and this is the input side, and this is the output side. Okay, this is a common collector, AC signal. Just they have removed the capacitors and they have modified this one. If you see, same diagram, but we are not keeping the internal resistances and capacitor, coupling capacitors. So this is an input voltage and this is output voltage where we are going to collect. So across this one, we are going to connect the load resistance. Across the load itself, the voltage will be you're going to get more voltage. That is amplification. Okay? So this is one diagram for AC signal amplification. So if you are making like the diagram, how you are going to write down the voltages as, this is the base current, this is the emitter current, this is the collector current. The direction is not. If you see, the emitter current is nothing but a combination of a base current and a collector current. Anyway, for any configuration, this is an NPN transistor. Okay, therefore the formula is not going to vary. Emitter current is equal to collector current plus base current. So this is VC, the collector to emitter voltage, VCB, collector to base voltage. Now this voltage is the input voltage. Okay, and this voltage will be your output voltage. Clear? This voltage in a common collector configuration, this voltage is input voltage, this voltage is output voltage, because you should not write here, you could not consider VP as input because emitter is not common. Okay? Emitter is not common. There will be a voltage, but that is not input voltage. Okay? So we are going to collect the output across this. This is the output. Okay? So that means if you are seeing some characteristics or some circuit, characteristics are not going to vary anyway, because only the design have been changed. That's it. Don't get confused. They have shifted the collector to the top and emitter to the bottom. But if you need to see the internal resistances, right, or RB and RE. Okay. So for example, if you are seeing this circuit anywhere, you should not think this is a common emitter. Okay, you can able to think this is a common emitter only if there is no RE here. Okay, if we have RE, that means we are going to collect the output voltage here. That indicates it is a common collector configuration. Okay. So now we'll try to discuss about, this is about the common base, common emitter and common collector configurations, and also how we are going to redraw the common collector configuration also have shown you. Just keep those points in your mind. No need to draw anywhere. Just keep those points in your mind. But anyway, the circuit is this one only, keeping the collector as a common. We'll try to compare the common base, common emitter and common collector configurations. First of all, base is a common. Base is a common. You see here, the base is common, common base, emitter, common collector. Input is emitter and output is a collector. The remaining two terms here. So, okay, base is input and collector is output. Here also, base is input, emitter is as output. Okay. So we could also call, in place of common, you can also call it as a grounded, because we are making that as a ground. So grounded base configuration, grounded emitter configuration, grounded collector configuration. If you are trying to make it, if you are finding the gain factors, alpha is for common base, beta is for common emitter, gamma is for common collector. So output current divided by input current. These all are output current divided by. So output current is the collector current, input current is emitter current in case of common base, and in case of common emitter, output current is the current, input current is the base current. In case of common collector, emitter current is the input current, so output current, and base current is the input current. Okay, these are the formulas for the gain factors. Okay, current gains. So this is actually phase shift. This phase shift is between the input and output. If you are giving an AC signal, how the phase shift is going to take place. If you see the 0 degrees, that is, there is no phase difference. Okay, but whereas we have only phase difference in case of common emitter configuration, that is 180 degrees phase difference. So this you can able to see when you are doing the AC bias, that is amplification purpose. Okay. And coming to here, the input impedance, if you want to calculate the input and output impedance, you can also calculate from the input and output characteristics also. So input impedance is low in case of common base configuration, and it is high in case of common collector configuration. Okay, output impedance is high in case of common base configuration and low in case of common emitter configuration. So you need to remember only the 2 points. One point is input impedance is high in case of common collector, output impedance is high in case of common base. If you know these 2 points, you can able to write, you can able to find out the remaining points. Okay, so impedance is high in case of common collector and output impedance is high in case of common base. Similarly, coming to the gain, that is gain is nothing but alpha, beta, and gamma. We see this is a very high gain. Okay. This is a very high gain value. This is a moderate, and this is a low current gain value. Okay. So high gain value means the value I have already told it is approximately more than 1000 like that. It is nearly 500 into 1000 like this. It is very less value because alpha, which we are going to get approximately 0.9 to 1 like that. Okay. So current gain, just like a voltage, current gain, we also have a voltage gain. Voltage gain is output voltage divided by input voltage. Okay. But in this case, it is a reverse case. So wherever you have a high current gain at that side, you're going to get the low voltage. Okay. Wherever you have a low current gain at that place, you're going to get. These are the applications. Best amplifier, that is best amplifier is always a common emitter amplifier. If you want to pick an NPN transistor, you need to choose the common emitter configuration only for the best amplification purpose. Either it is a DC bias or AC bias. And the common base is going to use as a constant current source, and common collector is going to use as a buffer. Buffer is nothing but whatever you are giving input signal, it will be appear across an output. We are going to call it as a buffer. Okay, it's some electronic circuits. We are going to use this as a buffer. So these are the 9 different conditions or parameters which differs the common base, common emitter, and common collector configuration. Okay. So this is ending concept up to BJT. So please all of you go through all the concepts, and I think we have covered almost all the concepts in the BJT configuration. And it is a very, very important and also very easy concepts. Please go through again and again. I have told yesterday that I will send you the questions, but I have not sent because of some other work. I will send you today. Okay. So team wise, I am going to give you the 2 to 3 questions. You can send by this weekend. Okay. Okay. Whatever you have doubts, you can ask me in the chat box. 10 minutes more. So if you want to revise from starting to ending, we can revise once. Sorry, came out of. Okay. So coming to the BJT, BJT is a bipolar junction transistor, which it contains with the 3 terminals, emitter, base, and collector. So we have PNP transistor. In the PNP transistor, N is going to act as a base. In the NPN transistor, P is going to act as a base. Okay. So anyway, the first junction emitter will have a heavily doped. The base will is a very lightly doped, and next collector is a moderately doped. Okay. We have also seen the operation of an NPN transistor and also the PNP transistor. After the operating principle, symbols, and also how the transistor is going to act as an amplifier. For an NPN transistor, it will come from base to emitter, and for PNP transistor, the current direction is from emitter to base. That is the difference. And how it is going to act as an amplifier also we have discussed, considering the common base configuration as an example. Okay. So then after we have discussed the 3 types of configurations: common base, common emitter, and common collector. For every configuration, we have drawn the diagram, and we have drawn also the characteristics of input as well as output. And at last, we have compared the 3 configurations: common base, common emitter, and common collector. So for every configuration we made, the emitter based junction has a forward bias, collector based junction has a reverse bias. Okay. We also have a 3 to 4 region. The first region is an active region, where the emitter based junction is a forward bias, collector based junction is a reverse bias. We also have a saturation region where both the junctions will be forward biased. Cutoff region where both junctions will be reverse biased, and Inverse active region will also be there, where the emitter based junction is a reverse bias and the collector based junction is a forward biased. Okay? So we are going to use the active region for amplification, saturation and cutoff region just like a switch. That is, switch on for saturation, switch off for a cutoff region. Okay? So these are the things. Almost 50% completed in case of 50 unit. We have left with the JFET. Okay, we'll discuss this JFET from the tomorrow session. So if you have any doubts, please ask me. You can message me in the chat box. If not, anyone requires to share with respect to your voice. That is, if you want to ask orally rather than chat box, you can give me a message that I will unmute you. Only you participant. Only 25 members came. Is Hassan present? Bindya, Raju. I think Hassan is not there today. Is Ashmita there? Hassan, okay, are you there? Okay, okay, Hassan. Okay, can kindly send me the attendance, Hassan. Okay. Okay. Right. Okay. All of you, thank you. Thank you so much.